Okay, good afternoon, everyone. It's 12:10 and time to start our today's Astro PH. Today we have three presenters, Sherry, Chakri, and Vignesh. Who wants? Sorry.
Can I go first?
Yes.
So I have one thing I want to discuss with everyone. So tomorrow at NTHU, we have Kajita-san's Nobel Prize talk from 1:20. I thought the time is a little bit tight, so I was thinking maybe we cancel tomorrow Astro PH. But I want to hear NCHU people's opinion because the talk is at NTHU. So NCHU people are really motivated. Of course, we should do it. Vignesh, do you want to do Astro PH tomorrow?
I'm okay to cancel, Professor.
How about Mohan? You really want to do it, right?
Not really. If
Chakri, you want to do it, right?
Yes, Professor.
Okay, so is it okay to cancel tomorrow Astro PH and then continue on Thursday? Any comments or opinion? Tezu-san, is it okay to cancel tomorrow?
I'm sorry, my speaker was broken, so tomorrow we skip.
Is it okay?
I'm okay, yes.
Okay, so let's skip tomorrow Astro PH, and then I encourage everyone to go to Kajita-san's Nobel Prize talk. Okay.
Okay.
Okay, so let's start today. Thank you.
Thank you, Thomas-san. So tomorrow we don't have Astro PH. So for today, who wants to go first? Thank you, Vignesh.
Let me share the screen. So I have posted the paper both in Google Sheets as well as Facebook page. So please have a look at it. So yeah, this is a very quick paper, but an interesting one. So they are talking about finding the spectrum of this persistent radio source associated with this particular FRB. So before that, I would like to give a quick introduction on what is called as persistent radio source. So basically, it's for each for mostly for the case of repeater FRB, there is an persistent emission of radio waves that is coming from a source very close to the repeating FRB. Those kind of sources are often called as persistent radio source. So these are like these have an radius of like parsec scale radius, and mostly have non-thermal emission mechanism. And yeah, so there are only few, I think there are only four such associations between a persistent radio source and an FRB, especially a repeating FRB. And here we are trying to understand the spectrum of this PRS for this particular repeating FRB. Why? Because just like the progenitor mechanism of FRBs are elusive, the PRS, we don't know what mechanism causes these kind of PRS emissions. So by studying the spectrum, we can constrain the progenitor types of these kind of PRS. That is the aim of this paper. So yeah, for that they use two telescopes. One is UGMRT, and actually they use three telescopes tracking a different frequency range. One is UGMRT at 1.26 gigahertz, and followed up by 6 gigahertz VLA telescope. However, for the case of low frequency part, they use LOFAR to obtain the spectra. So this gives a complete spectrum of from 144 megahertz to 6 gigahertz when they combine all the telescopes. Yes, so however they have detected the source at 1.26 gigahertz to 6 gigahertz using both the telescopes like UGMRT and VLA, but they couldn't detect the PRS at low frequency measurements from low far, which suggests that there is a sign of broken power law spectrum that makes this satisfies this absence of detection at a low frequency. So yes, apart from that, they estimate the age of this particular PRS candidate to be around 250 year, and the radius of the candidate around 0.4 parsec from the target. So what they claim is that these spectral shapes indicate a theoretical explanation which favors an magneto-ionic nebula, especially magneto-ionic wind nebulae that is inflated by a supernova ejecta, and which has a young magnetar inside that ejecta. So this theory can explain the spectrum that is obtained using these telescopes. So yes, I'll quickly move on to this particular FRB. I'll introduce this particular FRB, which is localized to milliarc second precision, and it is localized to a dwarf star forming galaxy. Interesting thing to note that is that all the PRS associated FRBs are located in dwarf low metallicity star forming galaxy, and similarly this FRB is also located in a dwarf low metallicity star forming galaxy at a redshift of 0.12. So yes, for the case of, I guess, for the case of flux measurements, I mean, firstly, for the case of data, they have used two telescopes, UGMRT and VLA. And this is the figure one. You can see that the image obtained from the two telescopes. The left panel is UGMRT at 1.26 gigahertz, and you can see that this is the position of this PRS, and the contours are the sigma lines, the confidence level lines at 3 sigma, 6 sigma, and 12 sigma lines. And the middle panel shows the VLA observation at 1.52 gigahertz, and the right last panel shows the VLA at 6 gigahertz range. And yeah, the central frequency and other properties of the PRS is given by this tabular column you can see here, and this gives the flux of flux at each frequency. So in order to fit the observed spectra, they use Gaussian fitting to fit the surface brightness of this PRS. However, actually, there are previous studies that have dedicated in measuring the flux of this particular PRS at different frequency ranges. One such famous paper is this Ibik et al. 2024. So they compare their observation with this Ibik et al. 2024 and came to a conclusion that Ibik et al. 2024 has some inconsistency in the measurements due to the some primary beam attenuation. They forgot to calculate they forgot to include the primary beam attenuation and some technical things. So yes, now this is the crucial part I wanted to share. So when they try to fit the spectrum, they started with 1 to 6 gigahertz range, and a single power law can be fitted to explain this frequency range. However, when they since they don't have a detection at 144 megahertz, they had is a upper limit. So to match this upper limit, they extrapolated this power law spectra. Maybe I can show the image. Yes. So this is the image you can see here. So this guy from 1 gigahertz to the 6 gigahertz, this can be well explained. You can see all the data points are well within this best fitted line. And but in the case of low frequency at 144 megahertz, they don't have a data point per se, but all they have is an upper limit of 170 microjansky. So they wanted to fit this data point. So if they extrapolate this, then it gives us a 2 order magnitude of higher expectation. I mean higher expected flux at this 144 Jansky, 144 megahertz. Sorry. So for this part, what they are saying is this has a from this what they are claiming is that there should be a turnover frequency for this particular spectra, and they decided to calculate the turnover frequency using this equation 1 and performing Monte Carlo fitting, from which they obtain the spectral index and the turnover frequency and the normalized frequency, normalized flux for this particular PRS. So these are the values. So for the case of 1 to 6 gigahertz, the alpha is around zero point 0.2, and which gives a normalized flux limit of to 211 microjoules at 3 gigahertz. So from which they can also calculate the turnover frequency, which is estimated to be around 370 megahertz. Remember that this is an upper limit again. This turnover frequency that they calculated is an upper limit, not an accurate value, because if this observation is this observed upper limit data point changes, then that could lead us to change the turnover frequency value. So this turnover frequency is sensitive to this upper limit data point. So apart from that, they have calculated the luminosity distance to be around 601 megaparsec at the, and spectral luminosity around using this formula. They calculated the spectral luminosity and the values around 9.5 into 10 power 28 ergs per second. So yes, combining all these values and equations, what the main purpose is to understand the progenitor candidate, right? So they theorize a progenitor candidate, which is magnetized wind nebulae model, described by Rahman et al. 2025. What this author claim is that this model favors the observed parameters that we are seeing, and in this model what they are saying is that there is an expanding magnetized nebula which is surrounded by the supernova remnant, and inside the supernova remnant there is a young magnetar which has a longer period of 10 milliseconds. So this is similar for all other PRS candidates. However, there is an they didn't give a conclusive result from this paper, because this, even though this model,
Time is up.
yeah, sure. So yeah, this, they are saying that this model could be the most appropriate progenitor candidate for these PRS, except this model has some flaws, and they have discussed that in the later part. So yeah, that's all from me.
Okay, any questions, comments? So beginners, thank you. How does what's the physics that this magnet emit persistent radio source?
Sorry, Professor, I couldn't hear you clearly.
What's the physics of the radio emission?
What's the physics of the radio emission? They didn't talk about the physics of the emission mechanism, but they talked about what could be the progenitor candidate in this paper, which is that it has a magnetized nebulae, which is
Yeah.
around the supernova.
So how the radio emission comes from magnetized nebula?
For that, I guess I need to look at this paper, Rahman et al. 2025. In this, they haven't given a clear conclusion.
Okay. So can you show that radio emission figure?
You mean this one?
Yeah. So what is it's a magnetar. Magnetar is going to emit a charged particle, right? Not figure two.
Yes. Oh, figure 2.
And then it's going to hit the magnetized nebula around this pulsar, right?
Yes.
And then this is going to, because of the magnetic field and then charged particle, it's going to create a synchrotron radiation, right? That is shown here, figure 2. Does this look like a synchrotron radiation?
Yes, actually, they are. Yes, actually, in that sense, I guess they are talking about 2 scenarios. One is the the synchrotron radiation that you mentioned due to the relativistic electrons, and the declining path, this guy, especially at lower frequencies, they have a separate physics over there.
Why lower part is suppressed?
uh why lower part is suppressed, Hmm, I don't know, but I read it somewhere, maybe I forgot. So
Synchrotron self-absorption.
yeah. So yes, exactly, yes. The lower part is suppressed due to the synchrotron self-absorption phenomenon. So that
What is
that gives us the
what
two clear spectral index.
what is synchrotron self-absorption?
So usually at low energy, when the electrons have a lower frequency, the part of the radiation emitted by the synchrotron process is self-absorbed by the same electrons. So that process is called as synchrotron self-absorption.
Thank you.
Okay, thank you, Vignesh. Is there any other questions or comments to Vignesh?
Vignesh, sorry, I missed this point.
Yes, Tomaki-san.
Is this the first detection for the radio spectrum of this source? Is it right?
Yes, actually, in this Ibik et al. Paper, they have tried to measure these kind of radio spectrum. However, this author claimed that the Ibik et al. Paper is has some issues, and the observed spectrum is not that much accurate. So for this FRB, I think this is the accurate radio spectrum of the PRS.
Okay, thank you very much.
Thank you.
Do you know what is the size of this source?
Yes, actually, I didn't
Physical
know the
size.
size, but then I know the radius. Maybe 0.4 parsec.
Okay, thank you very much.
Thank you.
Okay, thank you. So let's move on to next presenter. I think Sherry wants to go next. Sherry,
Yeah, let me present my screen.
thank you.
Is it visible?
Yes.
Okay. So today I will be talking about this paper where they've presented one of the first comprehensive studies of galaxies in the early universe, focusing on redshifts between 9 and 16, which corresponds like really early galaxies. The main goal of this paper is to understand, or first is to obtain the ultraviolet luminosity function, and from which get the how the star formation is evolved during this pre-reionization epoch. In the introduction, they say that for many years, our understanding of early galaxy formation, it is limited by the capabilities of telescopes like the Hubble Space Telescope, Subaru, and Spitzer Telescope, which was only able to detect galaxies up to a redshift of 10, and only few candidates beyond that. And these studies, they show that number of galaxies, they also decreased as we go to higher redshift. And when the cosmic star formation rate, which is obtained from the UV luminosity function measurement, they also decline with as the redshift increases. But they say that there were major uncertainties, especially at these high redshifts, that is redshifts about 10, as these data are less and also uncertain. So after the launch of JWST, with deeper infrared sensitivity, they were able to detect galaxies up to redshifts of 20. And in this paper, uh, they were able to directly observe these early galaxies and test if these models of the galaxy formation fit within them. So the aim of this paper is therefore to use the first JWST data to identify galaxy candidates at redshifts between 9 to 16 and to measure these important quantities, which is the UV luminosity function and the cosmic star formation rate density. Okay. Now, to describe the data, they have used the early JWST observation and which is the ERO, early release observation, and the early release science survey. And this data set together, it covers about 90 square arc minutes of sky. And they also include multiple infrared bands and near infrared, NIRCam instruments. They have the data they were able to reach magnitudes around 29 to 30, which they were able to detect faint and distant galaxies. And in addition, they also had spectroscopic data from NIRSPEC, which they have used to validate certain methods in this paper, and some more data from the Hubble and Spitzer. So now I will talk about the method. From the multiband photometric catalog that they have created, to identify high redshift galaxies, the author they use this well-known dropout technique. This method it relies on the fact that the light from a distant galaxy it is absorbed at different wavelengths, and uh, it is absorbed at wavelengths shorter than this Lyman break. Due to this neutral hydrogen in the intergalactic medium. So as a result, these galaxies they drop out in certain filters. So here in figure 2, they have shown this clearly. It is a color diagram. And each panel, it corresponds to different dropout selection. First one is F115W dropout, which corresponds to a redshift of 9. And the second one is 150. And the third one is 200. These corresponds to redshift of 12 and 16 respectively. Here in this paper, they have applied a strict color selection criteria, um, and uh, and for after this color selection criteria, they have done a SED fitting, and they have used Bayesian SED fitting using the prospector model, and this is shown in figures below. Okay. Here, this is one of the SED fitting of a particular candidate they they have chosen. Mm, Wait, I'm sorry. Yes, this one. Yeah. So these candidates have redshifts of greater than 10, and they show that these data points, the blue curve here, it corresponds to the best fit high redshift model, and we can see like a sharp drop in flux in the bluer bands. And particularly in this paper, they say that they have chosen their chi-square value such that it is greater than 9. Um, yeah, it's greater than 9. Uh, while in previous studies, they have chosen chi-square value extremely lower than that. Apart, so after getting the SED fitting, I will now talk about the results. So the first they derive the ultraviolet luminosity functions for these high redshift galaxies, and to do this they carefully do um, uh, completeness, and they remove contamination using certain mock galaxy simulation model. Then they fit the luminosity function using two different functional forms, which is this Stetcher function and double power law luminosity function. And from this, they show that, yeah, here from this they show that this luminosity function at the redshift of 9 and 12, they are in good agreement with the previous results from Hubble and early JWST result. And also the number density, it follows expected decline towards the brighter magnitudes, but there are still quite brighter galaxies at larger number of galaxies at brighter magnitudes. The main comparison they have done here is comparing the two different models, the Stetcher function and the double power law model. The double power law is represented by the red solid line here. And from here they say that though the difference between the model is low, the double power law tends to fit it better. So they decide to go with the double power law. Further, they also explore the luminosity function as a function of redshift. And here we can see that the overall normalization, it decreases as the redshift increases from 4 to 16. So this they say that this could mean that the galaxy become lower or lesser and rarer at this earlier time. But when they fit this with some theoretical models, they say that the decline is not as steep as what was predicted from these theoretical models. Further, they also check the star formation rate and how do they vary with redshift. And here, this blue dashed line is the star formation efficiency obtained from the theoretical model, and they say that the star formation rate is higher than what it was expected. So they say that this could indicate that the galaxies at these earlier universe could be forming more stars than what was expected. And that our assumption for these models could be incomplete from from studying these observation. So they, in their discussion, they talk about what could be the reason between these increase in the star formation rate. And they first say that there could be a lack of star formation suppression, or the brightness of these galaxies could be higher due to these high star formation rate. And this star formation rate, it could not be suppressed by the ultraviolet background radiation, which could be present in this epoch, a pre-ionization epoch. And they also talk about investigate whether these bright galaxies could be powered by active galactic nucleus. But they say that with their morphological analysis, most of these galaxies, they rather look like a point source, which could they don't look like a point source, but rather like an extended source. So they rule out the possibility of AGN, and they conclude that the presence of these high star formation rate could be because of this a lack of UV radiation at this pre-reionization epoch. Or that they also mention that they have assumed top heavy initial mass function for their model, and that could also be another reason why their star formation rate values could be higher than what was predicted from the model. Yeah, so this is the summary of the paper. Is there any question?
Okay. Sri, so this paper is very famous. Why do you think this paper is famous?
Particularly because I think they have used the first JWST release data. And also, they were able to, they mentioned that this paper is the first one to talk about the luminosity functions at redshifts greater than 16.
I don't think so. There are earlier papers who did the same thing, but this paper is more famous than earlier papers.
Okay. I'm not exactly sure about that, Thomas. And then I only saw that they mainly talked about obtaining galaxies like greater than 16, which they said it wasn't in the earlier paper. Maybe I missed out certain.
Well, so okay, one thing is that this paper combined all the fields. The earlier papers only used their own fields, but this paper combined all the available fields. And then as you show in this figure, they performed a simulation. So earlier papers, including our own papers, they just select objects. Oh, here are galaxies, here AGN, here brown dwarfs, right?
Yes.
But they performed the simulation to evaluate the contamination.
True.
And then that's not, that's not, fancy work, but then that makes this paper, more credible. More people believe this paper. And I think this paper is one of the first one to highlight the problem of these galaxies. This is what you discussed, but in there's a figure, right? Compare the number density of figure 17. It's one of the clearest way to show this problem. So the blue are theory, red is observation. So theory and observation are inconsistent. They showed it more clearer way than previous papers. So I think these are some of the reasons why this paper is more famous than other papers.
Okay.
Okay, thank you, Thomas-san, and thank you, Shuri. Is there any other questions or comments to Shuri? If no, we can move on to Chakri.
Okay.
Thank you.
So today I'm going to discuss about this paper. So this paper, during this last FRB conference, they have presented a poster on this. So in this paper, they address a key problem of these radio detection experiments like ultra high energy cosmic rays. So why this radio detection? Like this air showers produces these constant radio emissions like geomagnetic radiations. It can be detected the more away kilometers, and the advantages are it is large effective area and cost efficient developments. But the main problem is the precise calibration of this antennas array is critical, especially for this interferometry. So the limitations of these existing calibration methods are the ground pulsars and the cosmic sources and the pulsars. So in this paper, they proposed a solution using this uh, drone calibration pulsar system. So of how this drone pulsar system works. So in this figure, we can see that drone carries a DGPS rover and a logger and the micro controller and the solid state pulsar generator and the high pass filters. And on the ground, there is a reference DGPS GPS base station. So the rover on the drone and the bias station works together with the provided um, with the works together to provide it the high accurate position information. See, the microcontroller receives the timing information, including the PPS, which is the pulsar per second, and from the GPS system. Then it triggers to the pulsar generators. The electric pulse in the drone is the shaped and controlled by the uh, filters, and finally the radio frequency is radiated by the uh, broadband bicone antenna. And this was shown in the figure 1. And figure 2, this is the drone pulsar during the calibration of TRAJO-EM in Antarctica. So one of the main thing is the pulsar transit transmitter. So this generates the controlled radio pulse from the calibration. So the key properties are the repetition rate is from the 1 to 40 hertz with a time uncertainties of zero point 0.3 microseconds with a peak voltage of 1.5 volts. And uh, yeah, we can see in figure 3 the waveform and the frequency spectrum of the generated pulses are shown, which demonstrating that the signal is broadbanded and suitable for the calibration. And for figure 4, it shows the transmitted signal after passing through the antenna system, confirming that the pulses remain stable and usable. And additionally, in figure 5, they shows the antenna characteristics, including its beam pattern and the polarization properties, which is important for the antenna, uh, which is important for calibrating the different antenna responses. And uh, another important part is the GPS. So uh, which provides a position accuracy at the centimeter level. And as the GPS provides an accuracy of 3 meter in horizontal and 10 meters in vertical, whereas this DGPS system consists of two GPS receiver. One is the base unit and other one is the rover unit. Base unit is placed at a reference position, while this rotary unit together with the transmitter and is placed on the drone. These two units are recorded by this GPS system simultaneously based on one reference position. So, and they compare this difference between this measurement on GPS with this DGPS. Whereas this DGPS significantly improves this distance measurement accuracy, and this high precision is essential because even the small error in the position can affect this calibration result. And the author also studies the radio frequency interference, since both the drone and the pulsar can introduce some noise, and this their measurements are shown in the figure 7, which indicates that while drone noise is negligible at sufficient distance, and the pulsar itself produces a strong interference. To solve this, they used a shield box that reduces this interference up to 40 decibels. And uh, and the system was tested with this Trajoy experiment, which is designed to detect the cosmic rays and these uh, neutrinos using these radio antennas. And uh, this antennas operates in the frequency range of about 180 to 350 megahertz and aim for the sub-degree angular resolution. So in this results, the author demonstrated that the pulsar works reliably. And mm, figure 8 shows the timings of the pulsar is stable and transmitted power can be precisely controlled. So this confirms that system performance as expected. And finally, the accuracy of the drone position was validated using this interferometry. Uh, the figure 9, it is the reconstructed position from this antenna array, which is compared with this expected position from this GPS system. and there is a very small difference which is around 0.2 uh, and 0.3 in the elevation angle, which is within this required resolution. So this shows that system is accurate enough for practical collaboration. So the main conclusion is this paper presents a successful system of this drone based calibration system that is lightweight, portable, and with a high accurate. So it allows that uh, the calibration from any direction, which is major improvement over these methods. So this system can significantly enhance the performance of the radio experiments for detecting the ultra high energy cosmic rays, and it has a strong potential for future applications and for the large scale observations. So yes, this is the main conclusion of this paper.
Thanks, Jeffrey.
Yeah.
What is the difference between pulse source and a pulse board?
Oh, pulsar source and
Pulse source and a pulse board in figure 3.
so uh,
Well, actually, it's explained in the caption. But then my question is, so in a pulse source, it reaches high frequency, 800 megahertz or so. But then pulse board is sort of, disappearing around 600 megahertz or so. Can we use this at what frequency? So if we want to test at 800 megahertz, can we use this?
so this pulsar board for 800 megahertz.
Yes.
Yes, we can use it.
How do you know?
Um, so actually, I was reading this paper now. I did not complete another paper, so I was presenting this paper now.
What's the frequency range of bicone antenna?
So the frequency range is 150 to 350 megahertz.
So that's the limit. I think I'm a little bit worried that it might be only up to 350. It's a little pity, no? Your antenna goes to 800, right? Your burst antenna, but this is up to 350. Anyway, just my comment.
Actually, I was reading another paper, but I could not able to finish it, so I was presenting this.
Okay, thank you, Chakri. Is there any other questions or comments to Chakri? If no, we can. For tomorrow, we have no Astroph. We don't have Astroph, and for Thursday, Terry and Manogna are already volunteered, and we need one more volunteer for Thursday. Right? Or okay. So Mohan, it's better to move to other days. Okay, for Thursday, we have Rog, Terry, and Manuga. So, is there any specific questions or comments before closing the meeting? If no, we can close the meeting. Thank you for your attending, and see you on Thursday at Astroph.
Thank you.
Thank you.